So my name is Mylene Receveur. I'm a geothermal scientist at the British Geological Survey, and I'm going to present some results of research work that we've done in collaboration with the Mining Remediation Authority, which all started from very simple questions. What is the thermal recovery factor in mine water geothermal systems? So thermal recovery factor and volumetric heat-in-place methods are commonly used in conventional geothermal systems like aquifers. But what we came to wonder is, like, are they meaningful for mine water geothermal systems? Because we know that mines are really complex in terms of their geology, their hydrogeology, and of their recharge. And as we've seen from, there are many different parameters coming into play for that. And as we've seen from all the presentations before and yet to come, there are many different types of systems. And those are complex, but there are also for opportunities for different kind of utilization and different, there would be way with the design of a system to optimize that utilization and optimize the output we could get from it. So what we decided to focus on is the concept of sustainability. How can we sustainably recover heat from it? And how, in our case, and the focus of this study, how can data support the resource estimate and inform the designs of those systems and anticipate the output we can get? So we focused on looking into UK data. So here, just the background, the volumetric heat in place that we usually use focus on estimating what is the heat content in a certain volume of rock, considering both the volume of rock and of water and the thermal properties of these. In mine water system, usually, like in the past, studies have focused a lot on what is the actual volume of water in the mine workings, because this is what we would extract. So what is the heat in there? Some others consider the volume of the materials within those mine workings, which would have collapsed. But if you think about extracting for a longer period of time, the heat is going to diffuse above in the fracture zone above, which has its own volume and permeability. And over the very long term, this heat is going to propagate even further within the overburden. So in the end, the volume of heat store that you would access is much bigger than in the beginning. And of course, the challenge is that we are not really sure what is the volume of this of these units and what are the properties. And then what we get on the surface, the heat we can extract from this mine water is usually using this equation, so which depends on the temperature of the mine water and the flow rate at which we extract it. So the question in the end is, what is the proportion of that heat we get on the surface actually taken from the volume of rock in the underground? And that really depends on what kind of system we have. So on one hand, we would have a system with discharge. So usually those employed in this mine water treatment scheme, we want to maintain a water level at a certain level. So if we pump and the recharge is balanced, then we would get a constant heat output. But if the recharge is balanced, we could have a very sustainable system over the long term, as long as we don't pump more than the natural recharge can sustain. And on the other hand, the other extreme, imagining a system with reinjection, we could have the exact same system, but because we induce a thermal breakthrough, then there would be a huge unused potential from our system. So looking at data based on this, we're going to focus first on system with discharge and what makes it sustainable. So this is a great example from the Fife coalfield in Scotland. Their pumping started in 2004 to maintain the water level at an agreed level. And in 2016, pumping was added in Frances at 120 liters per second to support the pumping that was already in place at Michael. So we can see from the graph, the top graph, with this pumping rate at both sites. Despite the yearly fluctuation, the water level is quite similar at both sites and pretty constant over many different years. And the temperature at the bottom here is constant as well. So this long-term monitoring is a great data set that would allow us to calculate the recoverable heat. And we can see on the bottom left, this is the yearly rate extractable heat that was calculated assuming this total flow rate plus a 5 degrees delta T. And it represents only a small proportion of the volume that was of the heat that was estimated within the volume of mine water. On the other hand, we have an example from the Cranton mine water block in the Lancashire coalfield. Here, it was only a very small flow test that was conducted over 2 months. And we can see that with a very small pumping rate going from 2 to 4 liter to 6 liter per second, a step test, that it induced a very important drawdown over a couple of months from 6 to -8 meter above ordnance datum. And it was estimated that it would take more than a year to recover to this initial level. So in this case, the thermal output would be very small, but the sustainability would be limited by the hydraulic conditions of the system, which make it unsustainable. The third case is the case of a thermal breakthrough, but I'm going to focus on this in a case for a system with reinjection. So what make it sustainable? So there is an example of Gateshead that we've been talking before, and here I just want to show the example of the UK Geoenergy Observatory in Glasgow. This scenario where a few tests were conducted at the observatory, where we would abstract water from the Glasgow upper seam and re-inject in the Glasgow main, situated deeper. And in those scenarios, the results showed that there was limited pressure buildup or drawdown within each seam that would show that there is a great transmissivity in both of them internally, and no thermal breakthrough, which means no direct connections between the different seams. So same again here, using the rates for those specific experiment, we would see that there would be only a small proportion of the total heat estimated for the whole system that would be used. So this shows that there is a great flexibility using a doublet system to recover heat. And there are other cases for the same system. If there would be a pressure buildup, there are risks of collapse or unstable system. And this happened in the past in Gateshead, but solutions were found to manage this risk. And finally, for the same system, so we're still here in the UK Geoenergy Observatory. So I'm not going to extend too much about it. Alison is going to present just after on this specific experiment, but it's just to show that within the same system, the design has a real importance, because here we had a couple of tests intra-seam with injection and re-injection, injection and production in the same seam. And over a few days, a thermal breakthrough was measured at 12 liter per second. It happened after 4 days in the Glasgow upper, at 2 days after 2 days in the Glasgow main. So again, this is dependent on the heterogeneities of the system. And despite here again only a small proportion of the heat was recovered on the surface, the final message here is we can see that there is a great interplay between all the parameters, which means the system design, the hydraulics, all the thermal conditions of the system. And it all impacts how sustainable our system can be. So yeah, sorry, I'm getting completely lost. So I will conclude on that, on the fact that we do have a very complex system, but they all offers opportunities if the design is well understood, and data are really important to support. First, at small scale, understand the dynamic very close to a borehole, but over the long term, inform on the behavior of the system. And yeah, many opportunities.